Alright, now we're moving down along the line again, and we're going into the second derivative and seeing what that's going to be telling us. And once again, that's telling us about the concavity of our original function. I need to look at the second derivative now, so what I've started to do is I took my function, I've derived it once, that's what I found out in that last step that I just did. And now I'm going to be deriving my first derivative. I'm going to be basically finding the rate of change of my first derivative, because where my first derivative is increasing, that's where it's going to be concave up. And then when my first derivative is decreasing, that's where it's going to be concave down. So in other words, where my second derivative is positive, concave up. Where my second derivative is negative, concave down. So I am going to have to simplify this all out. So here I've gone ahead and I just FOILed this piece out, and I got this right here. I am eventually going to distribute that negative 2x to each one of those, and then minus. This is where I just combined these two terms. I changed the order in which I multiplied. So we got 4x times and then x squared plus 1. So here's where I kind of just simplified that, because I had 4x times x squared plus 1, and I brought it up here. I'm sorry, I know things are a little bit blurry. So I went ahead down here, and this is where I distributed these two factors together. I took negative 2 times everything, and then minus. Over here I had to FOIL that all out, so I got this whole segment, and then I have x squared plus 1 squared. And then so overall what I'm going to be getting is equals, and combining now these like terms, watch out for this subtraction of a negative. That's going to distribute, and then also subtraction of a, whoops, you can't see that last term, a positive. So just don't forget to distribute this negative, because I'm going to be subtracting off 4x in the end. And all of that equals positive 2x to the 5th minus 4x to the 3rd, and then minus 6x all over x squared plus 1 squared. Alright, so quite a lot of work just to find out where we're concave up and concave down. So I'm going to do my final answer right here is f double prime of x is equal to the 2x to the 5th minus 4x to the 3rd minus 6x all over x squared plus 1 squared. Alright, so in terms of finding out now, where is this function equal to 0 and undefined, I kind of cheated. So I knew I needed to set the top equal to 0. So 2x to the 5th minus 4x to the 2nd minus 6x equal to 0. And can't really just use the quadratic because we have a 5th root here. So what I did was I graphed it. And what I'm going to go ahead and do is, if you need to find out the zeros, here. To find out the zeros on your graphing calculator, don't forget you can go to second and then calc, so trace, and then you can say let's find the zeros. So you can go down to second, highlight that too. It's going to be asking for a left bound, you can kind of see that. So you're going to have to just take that cursor and move an arrow to the left of it. Make sure you're to the left of it. So I'm going to click left once more. To the left of that X, then it's going to ask for a right bound. Go to the right of it. Make sure you're to the right. I am way to the right. I've known that. And then it says guess. Just go ahead and hit a close estimate. What it says is my zero is at negative 1.70 or 1.73. So I'm going to go ahead and say that's where one of my zeros are. So at X equals negative 1.73, and then I'm going to do this twice more, and what I'm going to get is x equals 0 and x equals positive 1.73. Those right there are when the top is equal to 0. I will never get something for the bottom equaling 0, so my second derivative will never be undefined. But these right here are my inflection values. They're the possible values where it will change from concave up to concave down. So I am going to do a sign line for that. Say hi to Aldo, everyone. Okay, so here's my sign line. No, I won't. Oh, no. Aldo. Alright, so what I've done is I have gone ahead and I've plugged in these -2, -1, 1, and 2 values because they are points within the intervals that I've found divided by those inflection points. So when I do plug those into my second derivative, right here I plug in, for example, -2 in for my x in my second derivative. What I got was a negative value. So it's going to be, this is a place where it's concave down, concave up, concave down, and concave up. But these right here are my inflection points, so I'm going to go ahead and mark those now on my original function. Look how cute my dog is. Hey, Aldo. In those x values, and I've plugged them right back into my original function to get the y values of those. So I am going to go ahead and mark those now on my graph that I'm trying to sketch. So I'm going to go ahead and tape all of that work right next to my second derivative work. But I am going to go ahead and throw these points up there. You have -1.73, so right about here, it's at -0.4, so I don't know, something right about in that location. And then that's going to be an inflection point, and I should have done these in green because those are my critical points, but here we have 1.73 and then 0.74-ish. Okay, so there's the shape of what my function is looking like so far. And the last one now is to do the limits at infinity. So I need to try to find the end behaviors if there is a horizontal asymptote. Alright, so I'm going to be taking my y equals x over x squared plus 1. And I am going to be finding the limit as x approaches infinity of this function. And it's not really telling until I do that one manipulation where I'm going to locate the highest power on the denominator of my function, which is going to be that x squared, and I'm going to divide pretty much every single term on top and bottom by that x squared. So instead I'm going to be finding the limit as x approaches infinity, because what I'm going to do is take everything times 1 over x squared, and then everything times 1 over x squared on the bottom, and what I'm going to get is x over x squared, and then x squared divided by x squared plus 1 divided by x squared. What I get is the limit as x approaches infinity of 1 over x, when I simplify things, over 1 plus 1 over x squared. So now, using that property of 5.5, what you can then say is the limit as x approaches infinity of this piece right here, if I were to, I could substitute now in at this point. What you get on the top is 0 over 1 plus 0. So in other words, this thing is all going towards 0. As x approaches infinity, y is going towards 0. Same thing as if you did the limit as x approaches negative infinity, it'd be the same deal. We have 1 over x and then 1 plus 1 over x squared. So what's going to happen still as it approaches negative infinity, it's still going to be approaching 0. So what we have is a horizontal asymptote of y equals 0. So I'm going to post this up on my wall. Alright, so I posted that up on the wall, and now I'm going to draw in my horizontal asymptote. It's going to be, the end behaviors are going to be approaching 0 at the end. So I do know, this is what it's going to start to look like. I do know that as my ends get closer and closer, so now I am going to draw in my horizontal asymptote, which is going to be right on this line. And once again, what this represents is the line that the end of behaviors approach, but they never cross. So this was from my first step. It was finding the x and y intercepts. They were the shared point 0, 0. There were no vertical asymptotes. I went ahead then and found the first derivative, and in that first derivative what I was able to do was find the relative minimum and maximum. They're located in the green. So here we have the green points. I did change those. And then this was all of our work for those inflection points where it's going to change from concave up to concave down. So just keep in mind those were in the kind of light blue. And then finally the horizontal asymptote. So I drew that. When you're sketching this in, you know it's going to be a flowing line. Because there are no vertical asymptotes, it's a flowing line that's connected. The end behaviors are going to be getting closer and closer to this line. I didn't do that quite right. This should be a concave down because when you look over here it said from negative infinity to negative 1.73, it is kind of a concave down. So I am going to do something kind of arching halfway down. But then it's going to go concave up, and it's a flowing line that's going to be going through. Yes, it did cross the horizontal asymptote, but it can do that in the middle. We're only looking at the end behaviors when we're talking the horizontal asymptote. And then right here, it's going to switch from concave down to concave up. So it's going to start to kind of do a half bowl up as it gets closer and closer to the x-axis. So there is the sketch. If you do that on your graphing calculator, and if you look, we did it exactly. So all of these are using those steps. A lot of work. And I'll back up so you can see everything. A lot of work that went into these kinds of problems, but what I hope you can start to see is that it's all stuff that we've learned before, and you just have to kind of tie everything together.